So, hello everyone, welcome to Chemical Bonding YouTube channel. Today we will discuss a very important and interesting concept from carbohydrate chemistry. So, today we will discuss some basic concepts of aldoses. So, we will learn about structure of aldoses and how to remember the structure and the name of all aldoses. So, today in this video, I will show you uh, the easiest and you can say the simplest trick ever to remember all the structure of aldoses and also their names. So let's start. So aldoses normally carbohydrates contain aldoses and ketoses. So naturally occurring carbohydrates are mainly aldoses and ketoses. So aldoses are normally uh, monosaccharide. So aldoses uh, in the structure there is a carbon backbone and the topmost or you can say the endmost carbon containing a aldehyde group. So in aldoses there is a aldehyde group in the topmost or endmost carbon, and each carbon except this aldehyde group, each carbon in this molecule contain a single hydroxyl group. So in the case of ketoses, so there is a keto group instead of a aldehyde group. So now we will discuss today only about the aldoses. So there are many types of aldoses. So aldotriose, aldotetrose, aldopentose, aldohexose. So aldohexose means in that molecule there are 6 carbon. So including this carbonyl carbon 1, 2, 3, 4, 5, 6. Since there is 6 carbon, so that's why we call this hexoses as aldohexose. Aldo means there is on aldehyde group. Aldopentose means that compound that aldose contain 5 carbon 5 carbon atom. And aldotetrose means that aldose contain 4 carbon atom. Aldotriose means there is 3 carbon atom. So this structure we can simply write also again and again. Instead of writing this carbonyl CHO or OH group, we can write this in this way. This is the simplest version of writing aldoses or ketoses moieties. So this round head indicates that aldehyde group, and this bottom tail indicates this CH2 OH group, and this line this line both side indicates only OH group. So there is no in this structure we don't show that hydrogen, we don't show hydrogen, only we write here the OH group. So again I am saying that this round head is indicating aldehyde group, this CH2 group is this tail, and is this straight line this line indicating OH group is OH group. So aldotriose, this is general and simplest aldose. Aldotriose, so its name is D-Glyceraldehyde. So uh, D means I wanted to inform one thing that mm, that's the naturally occurring means the aldoses, the carbohydrates in aldose form exist in nature. All are D in nature. D in nature means, see, consider this aldotetrose. This is D-erythrose. So D means the bottommost chiral carbon. Top carbon aldehyde, carbon 2 containing on OH group, carbon 3 contain on hydroxyl group, carbon 4 also on hydroxyl group. So this is the bottommost chiral carbon. So if the bottommost chiral carbon is D in configuration, then it is called D-aldose. So since it is a tetrose, that's why it's called D-erythrose. So in this bottommost chiral carbon is OH is right side, then it is D. If OH is left side, then it is L. So if we take these compounds mirror image, then we will get L erythrose. L erythrose. So now come to the main points. So I am writing here that total 8 isomers, total 4 isomers, total 2 isomers, total 1 isomers. So see, in this aldotriose D-Glyceraldehyde, since there is only one chiral center, so we can say there is there should be two isomer, means there should be two isomer, means that is L and D. But we are considering this we are considering naturally occurring carbohydrates or aldoses, means we already know that in nature only uh, D aldoses are available. So we already know the structure or configuration of this carbon. We already know the configuration of this carbon, means this is D only, not L. If we have to prepare L, then we have to synthesize chemically. Naturally, only D-glyceraldehyde is available. That's why we are saying here one isomer. So theoretically there is two isomers, means L also L glyceraldehyde possible, but we know here that naturally occurring aldotriose is D-aldotriose, and that is D-glyceraldehyde. So this configuration is fixed. We already know that this is D configuration. That's why only one isomer, D isomer. So there is no question about L isomer, because in nature only D isomer is available. So aldotriose, that is D-glyceraldehyde, one isomer. Same thing, same concept applicable in this structure. See, 1, 2, 2 different stereo center, 2 different chiral center, means 2 to the power means 4 different isomer possible. Theoretically 4 different isomer possible, but we already know, I told you, I just mentioned that we already know this bottom chiral carbon configuration. That's why we are writing here D, not only erythrose. We are writing here D erythrose, means we already know this. We already know the configuration of the bottommost. All the aldoses, we all know the configuration of the bottommost. The configuration of the bottommost chiral carbon is fixed. It's D, means in every case, in every aldoses, the bottommost chiral carbon, the OH group should be in right side, and that is D in nature. If this is right side and that is D in nature, that's why we are writing here D glucose derivose. Assuming that, and not assuming, and it is true for all aldoses, naturally occurring all aldoses, the bottommost chiral carbon is D in nature. That's why we are writing D ribose, D glucose, D erythrose. So if this is fixed, so there is no question about this chiral carbon. So there is one chiral carbon. We can't say that this chiral carbon should be D or L, because that bottommost, we are writing here D ribose, D glucose, means the bottommost chiral carbon is D. Once one write one once someone says like D ribose, there is how many different chiral center, means there is D ribose, there is two different chiral center. He said that D ribose, means we have to understand that bottommost chiral carbon is D in nature, means that chiral center stereochemistry is fixed. So there is another two different chiral center, but we have so we have to think about the stereochemistry of these two chiral center. So since erythros, this chiral center, the stereochemistry is fixed D. So since there is only one chiral center, that's maybe D or L. So that's why two different isomer possible. So this is D and this is maybe D or L. So DD and DL may be possible because this should be D. There is no option for L, this carbon. There is no option for LD carbon. That's why only D is possible, one isomer. Here, this is D. This is D. No L for this option. So D and this chiral carbon may be D or L. So D or DL, two isomers. Similarly, in that case, this chiral carbon stereochemistry is fixed D in nature. So there are two different chiral center, means 2 to the power 2, 4 different isomer. 4 different isomer. This is fixed. Another two and other two different stereo center means 2 to the power 2, 4 different isomers. Similar things in this case, this stereochemistry is fixed, that is D. That's why D glucose, and there is other 1, 2, 3 different chiral center. So 2 to the power 3 means total 8 isomer possible. So I hope you understand. Now we will draw the all structure of all isomer of different aldoses, and I will show you the easiest and simplest trick to remember the structure, to draw the structure, and to remember the name of all structures. So let's move. So don't scare about that this slides, means there is a lot of thing I wrote, but I think within next 2 minutes you all understand and you all easily make in your copy you all easily you will make this type of structure, and you will easily able to write all the name and all the structure easily. So see, so this is D-Glyceraldehyde. So D-Glyceraldehyde means this OH is right side, so this stereochemistry is fixed. So this is D-Glyceraldehyde. This is aldotriose, means 3 carbon. Topmost carbon is aldehyde, and there should be 2 carbon, 1, 2, and 2 carbon. There should be on hydroxyl. There should be 2 hydroxyl group. So aldotriose, aldehyde, 2 hydroxyl group. So aldotriose. This is D-Glyceraldehyde. So in here I wrote KF reaction. So don't focus on that portion now. I will make another video, that is Killiani-Fischer reaction or Killiani-Fischer synthesis. So just remember what I am trying to say. I will make another separate video for this Killiani-Fischer reactions. So now just remember the way I am trying to say. So Killiani-Fischer reaction is a reaction. So when we perform these reactions on any aldoses, two higher homologues of aldose form. Means if Killiani-Fischer reactions will perform on aldotriose, then we will get two higher homolog, means aldotetrose to aldotetrose. So this is the simplest aldoses, means this is the simplest aldose, D-Glyceraldehyde, aldotriose, and Killiani-Fischer reactions. Just note the point, if we perform Killiani-Fischer reactions in a aldoses, we will get two higher homologs. Means higher homolog means if we perform Killian-Fischer reaction on aldotriose means D-Glyceraldehyde, that is aldotriose, then we will get aldotetrose, 2 aldotetrose. So now remember and uh, carefully see the way I am showing you and I am trying to say you. So this is D-glyceraldehyde. In Killian-Fischer reactions or Killian-Fischer synthesis, another point, that the one point is that from lower aldoses we will get two higher homologs or higher aldoses. Second point, we have to remember that higher homolog, the product of Killian-Fischer reaction, that higher homolog, there is same structure. The higher homolog, the structure, the stereochemical structure of the two higher homolog should be same from the bottom side. Means that is CH2OH. So this CH2OH from the bottom side, and the structure should be similar from the bottom side, and there is extra chiral center in the product. There will be extra chiral center in the product. So since we get two products, so in each product there will be extra chiral center, and that extra chiral center is different configuration in different product. Now I hope I am messing with you. So regarding this structure, so just remember that Killian-Fischer reactions, if we perform on a aldoses, so we will get higher homolog of aldoses. Means if we perform reaction on aldotriose, then we will get aldotetrose, and we will get two aldotetrose, two higher homologs. Aldotriose 3 carbon, higher homologs means 4 carbon, 2 chiral center, here 1 chiral center. So higher homologs mean aldotetrose, and we will get 2 aldotetrose. Killian-Fischer reaction, after Killian-Fischer reaction on aldotriose, we will get 2 aldotetrose. From lower homologs to we will get higher homologs. So the product, the structure of the product, and in this way I will show you the easiest way to drawing the all products. So the products of the higher homologs. So the in the products of Killian-Fischer reactions means the higher homolog, the structure or stereochemistry, will be same from the bottom side, from the bottom side, and there will be an extra chiral center just below to the aldehyde group. Just below to the aldehyde group, on chiral carbon, on chiral center is formed in two products, in two higher homologs. On extra chiral center is formed, and that is different in stereochemistry in the two products. If one is D, then in the other product it is L. So see, this is D-glyceraldehyde triose. Just draw a tetrose, means there should be 4 carbon. Topmost should be aldehyde, since we are discussing aldoses aldehyde, and the bottommost CH2OH. And see, in the reactant there is on OH. Bottommost chiral center OH means D. Just below aldehyde means the previously reactant chiral center, the chiral center present in reactant, just above that one chiral center will be formed, and If we placed OH group right side of one product, then in other product OH should be left side. I think you understand. So now this is D-erythrose and this is D-threose. So from D-glyceraldehyde we obtain D-erythrose and D-threose. Here is one chiral center, here is two chiral center. D-erythrose means this configuration comes from this and this configuration is fixed. So another new chiral center is formed, that is this. If one product it is right side, then other product it should be left side. So this is DD, this is DL. So D-erythrose and D-threose. So Killian-Fischer reaction, D-glyceraldehyde give us D-erythrose and D-threose. So these two structures are known as epimer to each other. Epimer means if in a molecule there are more than one chiral center, and they are differ only with respect to one chiral center. Means if any molecule there are 4 to 5 chiral center, the all the chiral center are same except one. If two compounds containing more than one chiral center and they only differ with respect to one chiral center. One chiral center means all the chiral center are same but they differ only with respect to one chiral center. Means one chiral center, if one molecule is D or R or S, then the other molecule it should be the different of different configuration. So if a molecule if two molecules, so I think uh, somewhat you understood what I am trying to say, that D-glyceraldehyde, aldose upon Killian-Fischer reactions will give two higher homologues mean aldotetrose. So we just saw that D-erythrose and D-threose are formed. The bottommost stereochemistry of reactant will retain in the product, but another extra chiral center will form in the product, and these two products differ with respect to that chiral center. The stereochemistry is different in two different product with that chiral center. So see, this is carbon 1, carbon 2. So we will say that D-erythrose and D-threose are epimeric at C2. Means D-threose and D-erythrose and D-threose, there are two chiral center, but the bottommost chiral center stereochemistry is same, and just they differ with respect to the top chiral center, means C2 chiral center. So that's why we can say that D-erythrose and D-threose are epimeric at C2. Epimeric at C2 means they differ only with respect to the stereochemistry of C2 carbon. Now see D-erythrose. So D-erythrose is aldotetrose. So D-erythrose and D-threose aldotetrose. So if we will perform Killian-Fischer reactions in D-erythrose, then we will get two homologue. So now I think you all understand that what will be formed. So D-erythrose is aldotetrose, so we will get two aldopentoses. So upon Killian-Fischer reaction, we will get two higher homologue, means since the reactant is aldotetrose, so we will get two higher homologue means two aldopentoses. So now you can easily draw the structure, I think. So I just told you that the bottommost in the reactant, the chiral center will retain in the product, but just below the aldehyde group there will form extra chiral center, and stereochemistry of that chiral center will be different in the two different uh, product. So easily you can easily, without seeing anything, without mentioning anything, without any hesitation, so you can easily draw the product. So this is aldotetrose 4 carbon, draw aldopentose, CHO top, CH2H bottom, 3 carbon in between that, 1 2 3. From bottom side DD, so draw bottom side DD, because this bottom two stereochemistry will retain in the product 2 2. In this product also draw a pentose, CHO, CH2H, bottom 2H should be right, because in reactant this 2H is right, means D. Just the top, the extra chiral center that is formed, if one OH is right, then the other product, that OH is left. Means if it is D, this chiral center configuration is D, then this chiral center configuration should be L. So D-erythrose will give ribose and arabinose. So this molecules, this aldopentose, pentose name is ribose, D-ribose, and this is D-arabinose. So we can say D-erythrose, which is a aldotetrose, upon Killian-Fischer reactions will give two higher homologues, that is two pentose aldopentoses, that is D-ribose and D-arabinose. So we also say here that D-ribose and D-arabinose are C2 epimeric in nature. See, there are three chiral center, but two chiral center, 1 2, the bottom two chiral centers are same in two product, but the topmost chiral center is different in stereochemistry in these two different product. So that's why D-ribose and D-arabinose are C2 epimeric in nature. They differ only with respect to C2 stereochemistry. Same thing applicable in D-threose. Now you can easily draw the structure. D-threose, aldotetrose, upon Killian-Fischer reaction, they will give aldopentoses, and we will get two product. In two product, from bottom side, one should be D, one should be L. So see, in the product CH2H, there should be 5 carbon total. Here 4 carbon, means upon Killian-Fischer reaction, higher homologue means 1 carbon elongation. So there should be 5 carbon. So CH2H, 1 OH right, 1 OH left. CH2OH, 1 OH right, 1 OH left. Other product CH2OH, 1 OH right, 1 OH left. So there are 2 chiral center. In the product there will be 3 chiral center. So just draw a chiral center just below the aldehyde group. If one chiral center, if you place 1 OH right, then you should have to place 1 OH left side. So from up to this structure will be same. The extra chiral center, if you place 1 OH group right side, then we have to place the other product, that OH group left side. So D-threose upon Killian-Fischer reaction will give D-xylose and D-lysose. So these are aldopentoses. Now you will easily draw the aldohexoses. I think within few seconds you will draw. So I think first, when you saw the first slide, I think you have scared, but now I think within 1 or 2 minutes you will draw the all structure like in this way. And you also, how I also show you within next 2 minutes how to remember this name. You have to remember this name in this way. Then you will find a proper way to write the structure, and also how to maintain the name of each structure in the following way. So D-ribose aldopentoses upon Killian-Fischer reaction, it will give aldohexoses. So we will get we will get two aldohexoses. So in this aldohexoses there is five carbon. So in the product there should be 6 carbon. So CH2OH and 3 chiral center, 3 OH should be right. Product CH2OH 3 chiral center, 3 OH to right side. Second product CH2OH 3 OH to right side. So the extra chiral center formed upon Killian reaction, that is top chiral center. If one OH group will be right side, then the other product, that the OH group should have to place left side. So D-ribose give D-allose and D-aldose upon Killian reaction. This is aldopentose. These are aldohexoses. So D-arabinose upon Killian reactions will give D-glucose and D-mannose. Same way, D-xylose upon Killian reactions will give D-glucose and D-iodose. Same thing, D-lysose upon Killian reactions will give D-galactose and D-dalose. See, this is 5 carbon aldopentose. In the product should be 6 carbon. From top carbonyl group, bottom CH2 is C without saying the product. C, you have to draw CH2 is OH right, OH left, OH left. Both product up to this same. CH2 is OH right, OH left, OH left. Second product CH2 is OH right, OH left, OH left. The extra chiral center form, if you put on OH right side, then other OH should be left side. So D-galactose, D-talose. So from D-glyceraldehyde, aldotriose, we will get D-erythrose, D-threose, aldotetrose. D-erythrose, D-ribose, D-arabinose. D-erythrose, D-ribose, D-arabinose. D-threose, D-xylose, D-lysose. D means the bottommost chiral carbon. Stoichiochemistry is D in nature and it is fixed. It is fixed. All the see, in all the aldoses, aldohexose or aldopentose or aldotetrose or aldotriose, the bottommost OH is right side. See, all this, the bottommost OH is right side, and that's why they are D in nature. So naturally occurring all the aldoses or ketoses are D in nature. So now the second interesting thing, I think you will understand how to draw the each structure, and now I am telling you how to remember the name. So you have to remember the name in that way. So not reshuffling any name from each other, but you have to remember this name I have written in this way. So now this is simplest, D-glyceraldehyde, and fast reaction we normally get two tetrose, aldotetrose, that is D-erythrose and D-threose. Up to this it's fine. D-glyceraldehyde, one OH right, only one chiral center OH right, D-erythrose one OH right, D-threose one OH right, extra chiral carbon one OH right, one OH left. So from D-glyceraldehyde we get D-erythrose, D-threose upon Killian-Fischer reactions. So aldotriose complete, aldotetrose complete, name and structure. Now from D-erythrose, I think now you can draw the structure, but name, how do you remember the names of that 4 aldopentoses? These are aldotetrose, they are aldopentoses. So first draw the all the structure like that, without any name, just draw the structure like that. From D-glyceraldehyde, assuming that you have to assume that Killian-Fischer reaction, you are performing Killian-Fischer reaction on this molecule, then you will easily draw the structure. Then consider this structure, and upon Killian-Fischer reaction, you will easily draw two structure. From this, you will easily draw two structure. Then again, assuming Killian-Fischer reaction upon this molecule, you will easily draw the 8 structure. So after drawing the structure, you have to remember two two sentence. So this sentence, I think, read this sentence 5 to 10 times. I think you will remember this. So first this one, ring all xylophones loudly. So ring all xylophones loudly. Ring all xylophones loudly. So ring ribose all arabinose. So xylophones, xylose, loudly lysos. So from this up to this structure, it is easy. D-Glyceraldehyde, from D-Glyceraldehyde, D-erythrose to its, you will draw the, I think that now after this 36-minute video, you will draw the structure of all aldoses easily. Tetrose, triose to tetrose, tetrose to pentose, pentose to 8 hexoses. But the name, but the name. First draw the structure in a page. First draw the 8 and 12, 15 structure, and now I think up to this there will not be any problem up to this. But after this four structure. So ring all xylophones loudly. Ring all xylophones loudly. First ring ribose. Second all arabinose loudly. Xylophones, xylose, loudly lysos. So all are D in nature. We have to remember that one thing, that all are D in nature. Bottommost chiral carbon is D in nature. Second, all altruists gladly make gum in a gallon tank. So all altruists gladly make gum in a gallon tank. All altruists gladly make gum in a gallon tank. All D-allose, altruist, D-ultrose, gladly, D-glucose, make D-mannose, gum, D-glucose, in D-iodose, a gallon, D-galactose, tank, D-talose. So these are the two sentences. Just speak 5 to 10 times. I think you will easily remember these two lines. And first you have to draw the 15 structure. I think you can easily draw the structure. You have to assuming that in every structure you are performing Killian-Fischer reaction. Then it will be easy for you to draw the each structure. And for name, D-Glyceraldehyde, from D-Glyceraldehyde, D-erythrose, D-threose. From D-threose, you will draw the two structure. From D-threose, you will draw the another two structure. You will get 4 pentoses. Now for pentoses, the name is ring all xylophones loudly ribose, arabinose, xylose, lysos. D, all are D in nature. From these 4 pentoses, we will get 8 different hexoses. Draw from this, draw the 2, assuming Killian-Fischer reaction, draw the 2 aldose hexoses. From this pentoses, draw the 2. From this, draw the 2. From this also, draw the 2. In this way, not reshuffling any other structure, not placing any other structure from each to any other. Just in this way, draw first. In every case, first draw the all DD. See, D, DD, DL. In this case also, D, DD, DDL. See, DLD. The extra carbon left side from each reaction, the extra carbon forming left side, you will make it D, and the right side is L. See, in this also the extra carbon I put here D, then L. From this, the extra carbon means topmost chiral carbon, that is new chiral center forming. I put in first D, then L. this from this first D, then L. From this structure, first I am putting D here, then L here. So if in this way you will draw first 15 structure, then you all know that from D-Glyceraldehyde we will get D-erythros, D-threos. Then without naming first, you just draw the structure the way I told just, and I showed you. Draw the structure and then uh, repeat this two sentences again. For aldopentones, ring all xylophones loudly, ring ribose all arabinose, xylophones xylose loudly lysos, all altruists gladly make gum in a gallon tank, all altruists gladly make gum in a gallon tank. Allose, ultrose, glucose, mannose, glucose, iodose, galactose, talose. So, we all know that all the carbohydrates, aldoses or ketoses, so they are 99% exist in cyclic form. Still, we have to learn some acyclic structure, their acyclic structure, and their nomenclature also, their name also. So, because there are so many reactions, so we have to show in acyclic form. That reactions we can show in the cyclic form. So you all know the ozone formation reactions, the oxidation, the reductions, so gluconic acid formation, glucaric acid formation, so and that the homologation means the degradations of chain, means rough degradation, whole degradation. So we will see that all the reactions in our upcoming video. So that's why we also have to learn some acyclic structure. So I think you all understand, and I think this video will help you a lot to understand, to draw the structure of every aldoses within 1 minute, and also to remember how to remember their name. So I think this video will be very helpful for all of you. So thank you for watching. Stay safe, stay healthy.